I believe it neither exaggeration nor mischaracterization to state that, for the unfortunate denizens of this particular planet, 2020 was a bad year. Luckily, the universe is a big place, and despite what our news media may suggest, Earth is not the only thing in it. So, let's decompress a bit, stretch ourselves outward, and see what the other 99.9999953 more nines, 7% were up to this year. But before we do, one note. NASA confirms that 2020 tied with 2016 for the hottest year on record, and the 2010s were the hottest decade. So yeah, 0.6003%. Get your act together. The cosmos pulls a fast one. In 2007, everyone went a little alien happy when a new form of extragalactic signal, a millisecond-long radio pulse, sometimes repeating, sometimes not, was identified in the cosmic drone. Given the poetic name of fast radio bursts, these signals were, of course, not aliens because it's never aliens. But over the last 13 years, identifying what they actually are has proven a somewhat Migrainian task. Luckily, they kept happening, and hundreds of subsequent observations have given us an ever more precise vision of their nature. And in 2020, we may have cracked it, or at least part of it. First, in January, astronomers, for only the 5th time, were able to pinpoint an FRB's source galaxy, the second such determination for a repeating FRB, and the first from a galaxy like our own. The FRB was apparently located in a star-forming region of a spiral arm of a nearby massive galaxy. Nearby as in less than 500 million light-years away. Using an array of 8 radio telescopes spanning a quarter of the globe, the team were able to obtain a resolution of just 7 light-years, the equivalent of spotting a human being on the moon. Narrowing down its location so precisely could allow us to finally isolate their origin. But the real breakthrough came in April, when the first FRB from within our own galaxy was detected by 2 separate telescopes. One, a $20 million Canadian radio observatory, the other, a backyard antenna jerry-rigged from cake pans by a doctoral student in California. The source was a magnetar 32,000 light-years from Earth. A magnetar is a very young pulsar, only freshly undead, whose surface, still spattered with the remains of its parent, seethes and rages into gargantuan magnetic storms of up to a quadrillion Gauss, enough to magnetize every atom in your body. Magnetars have been one of the leading hypotheses for repeating FRBs, since they are one of the few entities capable of generating such power more than once. The problem had always been that no known magnetar had ever generated an explosion powerful enough to register as an FRB from extragalactic distances. And then came SGR 1935 plus 2154, a magnetar located 30,000 light-years away in the constellation of Vulpicula. The burst seen from SGR 1935 produced 2 radio pulses lasting 0.585 and 0.355 milliseconds, 30 milliseconds apart, and released an astounding 10 to the 27 joules, 1,000 times more powerful than any magnetar eruption on record, and roughly the amount released by a 100-kilometer impactor. Whether these bursts qualify as an FRB has yet to be fully settled. The discovery was supported in November, when Bing Zhang of the University of Nevada observed a repeating FRB with the appropriately named 500-meter aperture spherical telescope, or FAST, located in Guizhou, China. He and his multinational team found that the repeating bursts were varied and individually different, showing different polarization angles. This would appear to rule out one-off events like supernovae as sources for FRBs, and point toward pulsars and their relatives as the culprits. So, once again, just as they did in 1967, pulsars have revealed themselves to be not aliens, but just as interesting. the quest for the origin of FRBs is not over. They may very well have more than one. Future studies opened up by these discoveries may well lead the way to a new realm of the universe. Voyager, a voice from the void. The Voyager program is the most successful space mission ever undertaken. It is solely thanks to one of its two extant probes, Voyager 2, that we have any detailed images of the last two planets in our solar system. Conceived in 1969 and launched in 1977, the Voyager mission completed its primary objective in 12 years, a relatively short time as space missions go. It was customary at that point to discontinue communication with the probes, as had been done with their predecessors, the Pioneers. But instead, a new idea began to form. Obviously, the cameras were now useless, but the remaining instruments, the ones used to detect invisible forces such as magnetic fields, were still very much in play. Thanks to speed assists by the gas giant planets, the Voyagers were far faster than the Pioneers, and had a fighting chance of reaching the outer limit of the heliosphere, the electromagnetic plasma bubble emitted by the Sun into interstellar space, before their instruments failed. How could anyone turn down a chance to sample the interstellar environment? In 2012 and 2018, respectively, Voyagers 1 and 2 crossed the heliopause, the outer boundary of the heliosphere, and entered interstellar space. The Voyager interstellar mission has already lasted nearly 3 times as long as its primary mission, and 2020 was initially expected to be the year it would terminate. Instead, the Voyagers, ever indomitable, continue to make unprecedented discoveries. In October, Voyager 2 confirmed a discovery made earlier by Voyager 1. When the craft crossed the heliopause, the surrounding matter density fell from an average of 3 to 10 particles per cubic centimeter to 0.055 and 0.039 particles per cubic centimeter for Voyager 1 and Voyager 2, respectively. But Voyager 1 would, roughly a year after crossing the heliopause, see particle density increase to 0.13 particles per cubic centimeter. And this year, Voyager 2 saw a nearly identical increase to 0.12 particles per cubic centimeter. One hypothesis for this increase is that material carried by the interstellar wind slows as it hits the heliosphere, creating a pileup. Another is that the electromagnetic fields create an unusually empty region just beyond the heliopause, which then thickens again as the field strength decreases. Far less expected was a signal received by both Voyagers, as reported by a University of Iowa team in December. They report that in 2014 and 2015, the Voyagers were hit by a shock of cosmic rays traveling through the interstellar medium at nearly the speed of light. It turns out that these cosmic rays were reflected off the heliosphere by the arrival of a shock wave from the Sun, the result of a coronal mass ejection months before. This reflection shot the electrons along magnetic field lines that acted like a railgun, massively accelerating the particles to 670 times the speed of the shockwave itself. Like thunder arriving after lightning, said shockwave hit the probes about a month later. While this magnetic acceleration mechanism had been discussed in theory, the Voyagers were the first to record it in the wild, so to speak. Just another wonder to add to their collection. The Voyagers are currently expected to run until at least 2025, by which time they will have been actively exploring space for nearly 50 years. Soon, it will be time to bid them farewell. I hope humanity will grant them a worthy eulogy. Titan's time. There's no way around it. Titan is another Earth, a dark replica Earth carved from ice. And since I consider Earth to be by far the most interesting planet in the solar system, every new fact teased out of that oddball world that some insist on calling a moon is to me like a laser pointer to a cat. And with Venus stealing the limelight from Mars this year, and Europa apparently in limbo until its dance with the Clipper, 2020 has seen Titan grab a quiet moment of its own. By far the most fascinating aspect of Titan is how it has somehow managed to replicate nearly every terrestrial process. Wind, rain, waves, even rainbows, with completely alien materials. Where Earth has rock and magma, Titan has ice and water. Where Earth forms seas, rain, and clouds from water, Titan forms them from methane. The biggest question remaining from Cassini's 13-year perusal of Titan has been whether Titan replicates Earth's most unique feature, ongoing geological activity. Do Titan's ice mountains occasionally erupt water lava onto its plains of hydrocarbon sand? Thankfully, even 3 years after Cassini's heroic plunge into Saturn's clouds, the data collected can still yield surprises. A study from Brigham Young University showed that craters near Titan's North Pole possess such telltale features as nested collapses similar to Olympus Mons, elevated ramparts, halos, and central islands. The association with the North Pole, where most of Titan's lakes reside, suggests that the lakes too might be volcanic features, perhaps flooded calderas. Similar features, though fewer in number, also exist on Titan's South Pole, which also features correspondingly fewer lakes. And speaking of lakes, one of the more curious facts about Titan is that, while lakes and rivers are currently confined to its poles, evidence for prior inundations exists all over its surface. When Huygens descended through Titan's clouds, it photographed what appeared to be a desiccated river system leading to a dry ocean. This year, that appeared confirmed by a team of researchers at NASA who attempted to discern the nature of the vague bright spots visible near Titan's equator, which Cassini could only image from a distance. Drawing on both Cassini and land-based telescopes, their analysis suggested that the bright spots could only be dry lake beds. As to why Titan's equator should demonstrate so much evidence of past rainfall, yet show no rainfall currently, well, it could be that equatorial rain is a seasonal event. And remember that on Titan, seasonal means once every 29 years. Like Earth, and for the same reasons, Titan has few impact craters. Those that survive the trip through its thick atmosphere are eroded by wind, rain, and geological processes. But Titan's peculiar geology means that the few impact craters remaining have unique features. This September, an ESA-led team examined Cassini data and found that Titan's impact craters can be divided into two camps, those amid the equatorial dunes and those in temperate mid-latitude plains. Those in the dunes, like the dunes themselves, are composed mainly of organic material. Those in the mid-latitudes are a mix of organics, ice, and frozen methane. Also, those in the mid-latitudes appear to be affected by rain, while those in the equatorial dunes appear to be simply covered by drifting sand. One of those smothered craters, called SELC, will be a target of NASA's Titan Dragonfly mission, set to launch in 2027. Much like craters on Mars, and on Earth for that matter, it should reveal much about the world's geological history. What measure us? Just how weird are we? Is our universe truly that envisioned by Christian monks in Asia's past? A hierarchy of life with us alone at the top, answerable only to deities? Or is our condition felt across the universe? On some distant world far from our star, do unnameable monstrosities make their gastropodal way to and from whatever passes for the office, pondering in their deepest hearts and spleens if they truly love their significant others enough to keep doing so? Until quite recently, the idea that we may be alone in the universe was restricted to morose intellectuals and ostracized freethinkers. Even before we filled our world with gods and angels, we still walked among elves, fairies, and sprites. As our eyes have become keener, so these beings have moved ever farther away, and now reside around distant stars, save for when they stop by to sexually assault the occasional outdoorsman. With the rise of SETI in the 1960s, it seemed we were on the verge of finally putting that question to rest. But after 60 years of searching, and no conclusive evidence, a creeping suspicion is coming over humanity. Could we be alone, after all? That conclusion seems bizarre, almost solipsistic, but in recent years it has attained mainstream acceptance. This year saw many discoveries and hypotheses in the field of alien life, some supporting the pessimists, some more optimistic, but all proving that the question of whether we are alone is destined to drive us mad. Of course, one of the frequent targets of the pessimists is red dwarf stars. Since they comprise 3 out of every 4 stars in the galaxy, demonstrating their habitability would vastly improve prospects for life in the universe. Except they flare. A lot. In fact, they superflare, regularly emitting bursts of light 1,000 times more powerful than our Sun. Given that any planets in a red dwarf's habitable zone would have to orbit perilously close to their star, often with a year lasting just 2 weeks or so, the likelihood of any managing to develop a complex biosphere would seem somewhat meager. And unfortunately, it just got meagerer. In October, a team at the University of North Carolina employed the Everyscope, a pair of gigapixel telescopes located in the northern and southern hemispheres, and NASA's Kepler successor, the Transiting Exoplanet Survey Satellite, or TESS, to observe over 300 red dwarf stars, in the process identifying 42 superflares. The most striking finding was that some superflares may actually attain temperatures 5 times higher than models had previously predicted, indicating that complex life, at least, would be a flimsy proposition on any orbiting planet. They do point out that as they age, red dwarfs do calm down, and there is no reason that unicellular life could not survive in such an environment. Given that red dwarfs live many solar lifetimes, ancient red dwarfs could still be havens for life. Also adding to the optimism, in December, a team from Northwestern University created an atmospheric and chemical model for planets undergoing intense flaring, and found that, quote, continuous flares actually drive a planet's atmospheric composition into a new chemical equilibrium, unquote. More importantly, they found that flares may not entirely eliminate atmospheric ozone, allowing life a slim chance to survive. But if red dwarfs are off the table, then we're left with stars like our own, orange K stars and yellow G stars. Unfortunately, our Sun isn't as average as some like to claim. It is, in fact, in the top 10% of stars in our galaxy in terms of size, and we now have some idea how likely such a star is to have an Earth-like planet orbiting it. By combining data from both Kepler, the most comprehensive planet finder in history, and Gaia, the most comprehensive star plotter in history, a worldwide team incorporating scientists from NASA and the SETI Institute calculated that the probability of a planet of between 0.5 and 1.5 Earth masses within the habitable zone of a G or K-type star is, depending on how optimistic you are, between 40 and 90%. This would mean that there are roughly 300 million planets in our galaxy in a situation roughly analogous to Earth, and that the nearest Earth-like planet around a Sun-like star would be about 6 parsecs away, which is roughly 20 light-years. Of course, this says nothing about age, atmospheric composition, geomagnetic field, or any of the dozens of other factors that may or may not play into whether a planet is habitable. And when you do, as a British team did this April, the numbers drop rather precipitously. The team essentially reran the Drake equation, but employing more modern terminology like habitable zone, and assuming that intelligence does not form around a star for its first 5 billion years. With all variables factored in, the total number of intelligent civilization in our galaxy stands at 36. Not 36 million, not 3,600, 36. Another depressing calculation was published in April by a team of researchers in Australia. We don't know precisely which planetary properties are non-negotiable for the development of an intelligent civilization, but 2 that are frequently cited are plate tectonics and a magnetic field. Plate tectonics acts like a thermostat for the planet, moderating temperature by cycling carbon. A magnetic field, of course, protects a planet from the peak of its star, shielding the surface from UV radiation and high-energy particles. Employing a model run through the Australian National Computing Infrastructure, and incorporating variables such as geochemistry, temperature, and distance from its star, the team found that the changing astrochemistry of the galaxy over time meant that it may have already spent its one chance to develop life-bearing planets. The current chemical makeup of the galaxy, compared to that when the Earth formed, is not conducive to the formation of planets with plate tectonics or a magnetic field. So the only Earths we are likely to find beyond our own are those that got a head start in the Great Galactic Foot Race. And since Australia seems determined to end our faith in the future, this year a team employing the Murchison Wide Field Array, a radio telescope in the Australian outback with an unusually wide field of view, conducted a classic, old-school SETI search, scanning 10 million stars in the constellation Vela for radio signals, and of course, found nothing. Though they were quick to remind us that, again, of course, despite covering 10 million stars, their search was the equivalent of looking for life in the ocean by staring at a single pond. Well, that was depressing. Let's move on to some happier exoplanet news. Exceptional exoplanets. These days, finding a new extrasolar planet is about as novel as finding a new star. To stand out, they must distinguish themselves in some way. Luckily, we're still in the era when every year brings an exoplanet first. Unluckily, my prediction last year that the top story of 2020 would be an exoplanet that ticked all three of the big boxes, Earth-sized, water-bearing, and in the habitable zone, failed to come true. But that doesn't mean the record books were blank this year. In September, astronomers using the venerable Chandra X-ray Observatory may have captured the first ever evidence for an extragalactic planet. Yes, really, extragalactic. The planet, if it exists, is located in the galaxy M51, aka the Whirlpool Galaxy, 23 million light-years from Earth. You might think that such a discovery would be impossible, and in most cases you'd be right. But it just so happens that the observed system, M51 ULS, is a binary between a star and an ultra-dense stellar corpse, either a black hole or a neutron star, that is currently in the process of consuming it. As it does so, it creates a small quasar, or superheated accretion disk, around itself that generates near immeasurable power, enough to be visible as X-rays from across the universe. And it turns out, anything is visible if it has a bright enough light behind it. For 3 hours, against the monstrous light of the quasar, the team observed a planet transiting. This event has yet to be seen again, but if it is real, the team estimates that it is about the size of Saturn. Also in September, a team using TESS believed that they may have discovered a long-standing staple of science fiction, a planet orbiting a white dwarf. To be honest, I'm surprised it's taken this long. The first exoplanets ever found were around pulsars, and their continued existence was harder to explain. The birth, if that's the right word, of a white dwarf is believed to be far less traumatic than that for a neutron star or black hole. It's not surprising that a planet could survive, though this object, at 14 Jupiter masses, strains the definition of planet and might be better described as a brown dwarf. It orbits its tiny parent, only about 90% the diameter of the Earth, in just 34 hours, a speed that suggests it migrated inward after the star's death. To our eyes, it would resemble Jupiter orbiting one of its moons. Perhaps the star's decreasing mass led to the planet's orbit becoming chaotic, or perhaps it was knocked inward by the gravitational interference of another planet. We won't know until we study the system in more detail. In October, a team from the University of Kansas employed TESS and the Spitzer Space Telescope to locate an exceptionally rare type of planet known as a hot Neptune. Hot Jupiters, Jupiter-sized planets that orbit their stars in less than a week, have been known almost as long as extrasolar planets. But Neptune-sized planets in similar orbits were rare enough for astronomers to coin the phrase hot Neptune desert. Neptune is often referred to as a giant planet, but that term is somewhat misleading. It is only 4 times the diameter of the Earth and 17 times its mass. Compare that to Jupiter, which is 11 times the diameter of the Earth and over 1,300 times its mass. It was long believed that the reason hot Neptunes were so rare was because their close proximity to their stars led to their atmospheres being blasted off by the raging fury of 3,000 kelvins. So to find a true hot Neptune with its atmosphere intact is akin to finding a 4-leaf clover. LTT 9779b is much cooler than expected, likely because its clouds are refracting a huge amount of the light blasting it. This world's very existence makes it a prime target for the James Webb Telescope, if and when it finally launches. Also in October, a team employing the Optical Gravitational Lensing Experiment, or OGLE, a Warsaw-based project that has been running since 1992, found what they believe to be the first Earth-sized rogue planet. OGLE scans the sky for gravitational microlensing events. Predicted by Einstein and now a workaday astronomical tool, gravitational lensing is when the gravity of a supermassive object pulls the light of objects behind it, drawing them into view like a natural telescope. This allows astronomers to see objects that would otherwise be beyond their capabilities. Unfortunately, microlensing events, those involving stars and planets as opposed to entire galaxies, are one-time only events. Once they occur, they never occur again, and so cannot be checked or repeated. The duration of a microlensing event depends on the mass of the object. A star can lens for days, a planet mere hours. This peculiar object lensed for just 42 minutes. No star was detected in the planet's light curve, which meant that it was either farther than 8 AU from its sun, or that it was not attached to a sun at all. The first Earth-sized rogue planet ever found. Our knowledge of rogue planets is set to explode. NASA's upcoming Nancy Grace Roman Space Telescope, a successor to previous infrared survey telescopes like IRAS and WISE, will likely find hundreds of them, and when she does, we will find them again. Current estimates, based on the probability of microlensing events, suggest there are more rogue planets than stars in our galaxy. We are about to unlock a dark layer of our universe. And speaking of uncovering dark layers of the universe, I want Planet 9 to be real. I think we all want Planet 9 to be real. And so far, to me at least, it is the simplest and most likely solution to the recently unearthed conundrums, in the outermost solar system. But at some level, it always seemed a bit bizarre, right? A planet larger than Earth with an orbital period of 10 to 20,000 years? How could such a bleak monster world even exist? Well, in December, after 7 years of speculation, a team at UC Berkeley and the European Southern Observatory, by cross-referencing 14 years of Hubble data with info from the Gaia satellite, have finally managed to clinch that HD 106906b, an 11 Jupiter mass object near a binary star system in the constellation of Crux, is in fact orbiting it. The most recent measurement for its distance from its stars is 747 AU, which is within the range predicted for Planet 9. Nor is it the only one of its kind. Up to 20% of stars are believed to possess similarly distant planetary companions. HD 106906b was actually discovered in 2013, though at the time it was unknown if the planetary mass object was in orbit around its stars, and thus a planet, or simply in common motion with them, which would make it a brown dwarf star. This was doubly confusing because HD 1 etc. b is part of the Scorpius-Centaurus Association, a loosely bound collection of about 430 young stars, all between 10 and 20 million years old, traveling in roughly the same direction, likely the last farewell of a stellar birth cluster. While the initial discoverers did note that the chances of the object not being in orbit around the binary were about 1 in 10,000, they still couldn't prove it observationally. But one fact makes this exoplanet truly fascinating. Besides its errant planet, the HD 1 whatever binary is also orbited by a gigantic 100 AU wide ring of dust, likely a solar system in formation. There is no way this exoplanet 9 could ever have migrated to its current position without utterly disrupting that dust disk, which leaves only two options for its formation. First, that it was captured from a sibling star when they were still huddled close in their birth cluster, as Mike Brown believes is true for Planet 9. Or, as the Discovery team suggested in their paper, the far more intriguing possibility that both it and its binary parent may have formed from the collapse of local regions of an interstellar gas cloud. In other words, HD1 etc. b is not a planet, but a brown dwarf star. Brown dwarfs are objects that formed identically to stars, but were never large enough to sustain long-term nuclear fusion. The traditional cutoff point between a brown dwarf and a large gas giant planet is 13 Jupiter masses, the mass needed to fuse deuterium, a heavier isotope of hydrogen, which, due to that isotope's relative rarity, only lasts for a short time, but enough to grant the aspiring gas ball at least temporary starhood. Except HD1 whatever b is only 11 Jupiter masses. Should we then call it a planet? A planet that formed like a star? Where does the line between star and planet truly lie? HD1 etc. b isn't the first object to blur this distinction. Astronomers have identified free-floating, quote, brown dwarfs as small as 6.5 Jupiter masses. Indeed, in 2003, the IAU officially coined the term sub-brown dwarf to deal with these problematic finds. But of course, a mere name does not resolve the issue. Just how small can a sub-brown dwarf get? As small as Jupiter? As small as Saturn? As small as Neptune? Those still aching over the loss of Pluto can rest assured. The definition of planet is far from set. As our knowledge increases, it will change, just as it has for thousands of years. Well, hello, Proxima. Look, of course I was going to talk about this. I mean, how could I not talk about it? It's just that I like to go into detail in my videos, and there's just isn't that much detail to go into right now. Heck, there isn't even a scientific paper published about it yet. Also, given how speculative my Proxima-centric videos tend to be even at the best of times, I didn't want to build speculation on what was already a fairly speculative result. So, all that aside, what exactly was it that the worthy souls at Breakthrough Listen believe that they found? Well, actually, from the looks of things, a lot. Breakthrough Listen, it must be said, do have a sense of history. Among their chosen telescopes are one at Green Bank, West Virginia, the birthplace of SETI, and the Parkes Radio Observatory in Australia, which played a vital role in tracking the events of the Apollo 11 moon landing. On that subject, if you can, check out the Aussie comedy The Dish. It's hilarious, if not remotely historically accurate. It was Parkes, on April 29, 2019, that first sniffed out that delectable signal, though oddly, they weren't intending to. SETI isn't just about collecting signals. It's also about the science of astrobiology and the constraints which the universe might place on intelligence elsewhere. To that end, BL had reserved Parkes to gather data on a subject with which followers of my Proxima series should be very familiar. Flares. As noted above, red dwarfs flare more frequently and violently than larger stars like the Sun. Since planets within a red dwarf's habitable zone would have to orbit far more closely to their stars than Earth does to the Sun, the impact of these flares on any nascent life could be apocalyptic. Since Proxima is both a red dwarf and the closest star to the Sun, it made a logical candidate for such a study. Breakthrough Listen turned the Parkes toward Proxima for 26 hours, looking for signs of solar activity. And then, a young intern named Shane Smith identified a spike at the razor-thin band of 982.002 MHz, a region of the EM spectrum largely ignored by our own satellites or spacecraft. The signal appeared to have no jagged edges, no depth, no personality. It was, as Breakthrough Listen head Andrew Simeon put it, just a tone, just one note. That was the start. The next step was to employ a technique called nodding, in which the telescope observes another part of the sky as a control to rule out any sources of terrestrial contamination. 5 of the observations saw the signal return when the telescope was realigned toward Proxima. Whatever it was almost certainly in Proxima's direction. The signal was christened Breakthrough Listen Candidate 1, or BLC-1. Rather oddly, it appeared to be shifting in frequency, like a Doppler shift, which you would expect from the motion of a planet, either our own or one farther away, except the shift isn't down toward the red as you would expect. It's upward toward the blue, as if it were moving towards us. Of course, None of this means that BLC-1 is artificial, or even that it came from Proxima. Breakthrough Listen are fairly unanimous in their opinion that whatever BLC-1 was, it had a human origin, perhaps a passing satellite. Or it might be a mundane natural phenomenon, or have originated far behind Proxima, or from any of the 100,000 other stars within the Parkes' field of view. Nothing can be said for certain until BLC-1 is heard again, which, in the nearly 2 years since it was found, it has not been. Until, or unless, it is, BLC-1 will go the way of the WOW signal, a maddening hint of a new world of gods and monsters, lost in the endless dark. Still too much universe. In my video, So Much Universe, So Little Time, I pointed out that our chronology of the universe is currently somewhat twisted. Our two principal means of finding the rate of the universe's expansion, the so-called Hubble constant, and thus determining its age, standard candles, objects of known brightness whose distance can be directly measured, and the cosmic microwave background, the glow left over from the Big Bang, have produced conflicting results outside the realm of simple error. For the tried and true method of standard candles, the results have converged around a Hubble constant value of 73 kilometers per second per megaparsec, which would make the universe about 13 billion years old. For the more avant-garde method of employing the cosmic microwave background, we obtain a Hubble constant of 67.7 kilometers per second per megaparsec, which would grant the universe an age of 14 billion years. This difference may seem fairly inconsequential when the thing being measured is, the universe, but the precise measurement of the age of the universe has vital implications for still unresolved issues in physics, in particular, the nature of so-called dark energy. And this year, attempts were made to break the stalemate by trying new and untested methods. One could argue they only made things worse. Not to nerd out too much, but the first attempt was, frankly, awesome as all hell. I never thought I'd have reason to write the phrase cosmic water lasers, but such are the joys of this job. So yes, in June, an international team employed an array of radio telescopes to search the sky for cosmic water lasers in the hopes of obtaining a different value for the Hubble constant. Apparently, steam in orbit around a supermassive black hole can produce stimulated light emissions in the microwave spectrum, or masers, called megamasers because of course they are, which are detectable provided the black hole is facing the Earth's side on. By measuring the time it takes the maser to traverse the disk, you can get an accurate estimate of the disk's size, and from that, its distance. Unlike the other two measurements, this is based on direct geometric calculations of the kind available to the ancient Greeks, and so should provide an answer independent of any previous systemic errors. And this year, the Megamaser Cosmology Project, or MCP, published their latest value for the Hubble constant, 73.9 kilometers per second per megaparsec, almost exactly in line with the standard candle measurement. In November, David Harvey of Leiden University calculated a value for the Hubble constant by employing a phenomenon almost as cool, gravitational lensing. When light is caught in a gravitational lens, it can arrive from multiple routes, creating duplicate images of the same object. In 1964, Norwegian physicist Sjø Revsdal realized that when a lensing object is off-center, the light from one image will take longer to reach the eye than from another image. So if the object, say an erupting quasar, has some repeating variation in its output, that variation will appear in one refracted image before the other. By comparing the distance to the object's redshift, an independent measurement of its distance can be found. And it is also 73 kilometers per second per megaparsec. Oh, but that's not the end. In July, the Sloan Digital Sky Survey released a compendium of 23 different scientific papers, summing up its 20-year attempt to map the universe across space and time. The largest of the surveys, the Extended Baryon Oscillation Spectroscopic Survey, or EBOS, examined the spectra of 1 million galaxies. Young blue galaxies, ancient red galaxies, even primordial quasaring active galaxies, essentially filling in the gap between the cosmic microwave background and now. These data effectively acted as a rerun of the Planck result in 2018, and they agreed with it, producing a value for the Hubble constant of between 67 and 69 kilometers per second per megaparsec. Also in July, another scan of the CMB using the Atacama Cosmology Telescope in Chile produced an identical result. It seems that no matter which technique we use, the early universe will always produce a lower Hubble constant than the later one. In one way, at least, this is a good result. It suggests that the values are not due to human error. In another, it's a nightmare, because it means that we may have to topple some long-cherished ideas about what exactly this thing we call a universe really is. Check your privilege. One of the founding tenets of modern physics, established since Newton overthrew Aristotle, is that we are not special. For thousands of years, the doctrine of geocentrism held that we were the focal point for the cosmos, the locus around which the cosmos rotated. While Aristotle viewed this as a natural consequence of the Earth's heaviness, heavy things fall and the lowest point in a sphere is the center, later writers would note its congruence with the first two chapters of Genesis, and its seeming evidence for God's design. Once the evidence for Newton's universe, and its required heliocentrism, became overwhelming, the Church quietly adjusted their cosmology, and everyone settled down until Darwin showed up. In recent years, science educators have for some reason employed this tenet to rub humanity's face in its collective insignificance. Hence why documentaries continuously describe our sun and galaxy as average, when they are in fact larger than the vast majority of stars and galaxies in our universe. Some call this tenet the Copernican principle, after the man often claimed to have proved the Earth moved around the sun. Personally, I object to this name. First, because Copernicus didn't actually do that. That honor, depending on your definition of proved, goes either to Edmund Halley in 1758 or to Friedrich Wilhelm Bessel in 1838, and also because, as an ordained Catholic canon, Copernicus would likely not have appreciated his name being used as a byword for cosmic existential nihilism. The cosmological principle, to give it its more neutral name, asserts that from at least one vantage point in the universe, our segment of it, however large, is identical to everywhere else. More eloquently, we do not have a privileged point of view. When viewed as a useful assumption rather than as an article of faith, the cosmological principle makes sense. When given a sample of one, it is perfectly rational to assume that it is typical of the whole. The problem is, so far, we haven't found that coveted vantage point. Our sun does not exist in a randomly distributed fog of stars. It resides in a highly structured galaxy, which in turn forms part of a larger structure called the Virgo supercluster, which in turn forms part of an even larger structure called the Laniakea supercluster. Relatively nearby, the Boötes void, a vast bubble of nearly nothing, 330 million light-years across, comprises a full 0.25% of the volume of the observable universe. The Hercules Corona Borealis Great Wall, a galaxy filament discovered in 2013, is roughly 10 billion light-years across, more than 10% the diameter of the observable universe. Cosmologically speaking, at least, our point of view is looking pretty privileged. And this year, we may have extended that privileged position to the universe entire, or at least the bit that we can see. In June, Leo Shamir and colleagues at Kansas State University used a number of the world's most powerful telescopes, including Hubble and Pan-STARRS, to survey the spin direction of 200,000 galaxies. There is nothing intrinsic to the spin direction of a galaxy. Viewed on one side, a galaxy will appear to spin clockwise, from another, anticlockwise. If the cosmological principle holds true, then the distribution of galaxies should be close to random, and the number of galaxies we see spinning in one direction should be equal to the number spinning in the opposite direction. Except, Lior found, it isn't. Not only do the observed galaxies' rotations differ by as much as 2%, but the variation increases with distance, and thus with time. It seems that early in the universe's history, galaxies were far more directed than they are today. The observations also suggested that the early universe had a number of different poles of direction, an assertion backed up by previous work with the cosmic microwave background, which had also hinted at such multipoles. But the possibility of forward contamination had rendered the results inconclusive. No such possibility exists for this data set, and it could be the first hint of something remarkable. On the other hand, in August, a much larger survey of 31 million galaxies, the so-called Kilo-Degree Survey, or KIDS, found that not only was the distribution of galaxies in the universe homogeneous, it was 10% more homogeneous than previously calculated. This result is so striking, it has led some to consider ditching our current cosmological models. There are a number of lessons to be drawn from this, I think. The first is that we are still a long way from a definitive map of the universe, and that all results should be taken with a silo of salt. The second is that the cosmological principle, whether or not it is supported by evidence, is pointless. To function, science, like all branches of philosophy, must rest on a number of foundational axiomatic assumptions, most of which, in science's case, boil down to the universe has rules, and those rules are the same across space and time. The cosmological principle is not one of those assumptions. Karl Popper, the founder of modern scientific philosophy, described the cosmological principle as, quote, dogma that should never have been proposed, unquote. Science doesn't need it, and it may be time to scrap it. At least we solved one corona this year. There are a number of scientific mysteries that, when mentioned to the layman, are likely to result in a double take, a puzzled pause, and a cry of, really? We still don't know that? Among them are, why do cats purr? What is time? Why do we dream? And why do we play music? While it might not be as immediately recognizable as those, nor as epically embarrassing as the cosmological constant problem, see my video, So Much Universe, So Little Time, for an explanation of that particular sore thumb, the mystery of the sun's corona, the ghostly atmosphere only visible during solar eclipses, and in particular its astonishing temperature, has been staring physicists in the face, and quietly driving them insane, since they first discovered it 80 years ago. One of the first things you learn when you're a child is that heat dissipates. Fire is hot, but merely warms a room. A match lit in the snow will not warm you as much as one lit inside. The sun is, of course, hot. Its core runs at a constant 15 million kelvins. Its surface, as you might expect, is much cooler, running at just 6,000 kelvins. You thus might justly suppose that its atmosphere would be cooler still, and, for the first 500 kilometers, it is, bottoming out at a mere 4,000 kelvins. But then, somehow, 500 kilometers from the surface, the atmosphere's temperature shoots back up, hitting roughly 2 million kelvins at the corona. This is the equivalent of walking through a dense bank of freezing snow and finding, hovering above it, a fog as hot as, 2 million kelvins. The gargantuan heat of the solar corona has stood for years as one of astronomy's most intractable and infuriating mysteries. How could we claim to understand the solar system if one of its largest structures was apparently violating the laws of thermodynamics? One of the problems of discussing solar phenomena is that they, as with all stars, are driven by electromagnetism, a strange and counterintuitive force that most of us will never see outside the black box of technology. Even explaining what we know for certain is difficult. The sun is composed of plasma, a form of matter in which the electrons of atoms have been stripped from their nuclei, making them electrically conductive. Both lightning and the aurora are plasmas. When two oppositely charged magnetic fields come into contact, their field lines connect, creating a kind of short circuit that releases a huge amount of energy. On the sun, this energy is released in solar flares, explosions of high-energy light that in 1 second can release the same amount of energy as the sun sends to Earth in 100 years. Solar flares are often confused with prominences or coronal mass ejections, the physical phenomena that accompany such releases of energy, but these are composed of matter, not light. It had long been assumed that such magnetic connections had to be responsible for the heat of the corona. In 1988, Eugene Parker, the discoverer of the solar wind, proposed that the corona's heat may be deposited by nanoflares, tiny explosions on the surface of the sun, a billionth the power of a typical flare, hence their name, and invisible to then-current telescopes. Models suggested that nanoflares could set each other off in massive chain reactions. This year, a team using NASA's Interface Region Imaging Spectrograph, or IRIS, a largely unsung solar observatory launched in 2013 specifically to solve the mystery of the corona, were able to identify tiny loops emerging from its surface, each less than 100 kilometers across, yet millions of degrees hotter than the surrounding surface. Models showed they could only be tiny solar flares. Turning to NASA's Solar Dynamic Observatory, the team then observed the corona, just 20 seconds after the flare's appearance, suddenly superheat to millions of degrees. The first evidence tying nanoflares to coronal heating. It will be a while before this result is confirmed, but it looks like at least one corona will not be troubling us for much longer. Life in hell. We are accustomed to seeing our world, Earth, as a loving, bountiful mother, though these days she comes across as a put-upon, ignored mum who's fed up with our nonsense. Not so her sister Venus, whom we have spent the space age demeaning as a justly barren harridan who beguiled us with her looks but repulsed us when she opened up. So convinced were we of the sterility of her fiery womb that we almost immediately abandoned her and turned our search for extraterrestrial life to Mars, Earth's older, crusty, decrepit husband. But in September, against all expectations, and arguably even logic, a team led by Jane S. Greaves of Cardiff University announced that they had discovered evidence for life in the mid-atmosphere of Venus. That evidence came in the form of phosphine, a phosphorus atom with 3 hydrogen atoms, essentially ammonia with an extra electron shell, initially measured at 20 parts per billion. In Earth's atmosphere, phosphine is measured at parts per trillion. This is because phosphine is extremely reactive, and in the presence of oxygen, or the radicals created by solar radiation breaking apart carbon dioxide, will quickly break down into more inert compounds. Phosphine is found in abundance in a reducing atmosphere like Jupiter, but an oxidizing atmosphere like Earth or Venus would break it down in mere hours. For it to be present in such quantities, something would have to be continuously producing it. On Earth, phosphine has 2 sources: factories and living organisms, particularly anaerobic bacteria such as those found in our guts. Phosphine can be generated inorganically by processes such as lightning, meteor impacts, UV, or volcanoes, but only in amounts a 10,000th of what was initially seen. In fact, a separate paper published earlier this year had suggested phosphine as a viable biosignature, precisely because it is so difficult to produce inorganically. The team's initial search, undertaken in June 2017, did not set out to find phosphine in Venus. It was intended essentially as a control, a null result to serve as a baseline for future searches. Analysis was tricky because Venus, which is bright enough to cast shadows, is also bright enough to cast reflections in a telescope, and so the team turned to the James Clerk Maxwell Telescope at Mauna Kea, the largest microwave telescope in the world, to identify the spectrum of phosphine in the infrared, both because phosphine produces a unique signature at 1 millimeter wavelength, and because catching it in the planet's own radiated infrared light eliminated potential glare. After 18 months and 3 rejections, the team finally confirmed the result with the Atacama Large Millimeter Array, or ALMA. The team initially placed the probability of the result being due to error at 15 sigma. For comparison, 1 sigma indicates an error probability of about 10%, while 4 sigma indicates an error probability of less than 0.1%. Those of you who watched my video on Venus, which was initially meant to culminate with this discovery until I overreached myself again, may recall that Venus's atmosphere mostly consists of a superheated ocean of liquid carbon dioxide topped with rolling fogs of sulfuric acid. But, as Carl Sagan pointed out 60 years ago, at altitudes between 50 and 60 kilometers, the atmospheric pressure drops to 1 bar, or Earth at sea level, and the temperature falls to a very Earth-like 300 K. And it is precisely at these levels that the phosphine detection was made. That's not to say that the environment would be pleasant. Even at that altitude, Venus's atmosphere is still a mixture of CO2 and sulfuric acid, and all but devoid of water or oxygen. So could life exist there? Possibly. Many microbes have been shown to exist quite happily in sulfuric acid, such as those residing in so-called snotites within hydrogen sulfide-rich caves, which excrete sulfuric acid as part of their metabolism. However, they still require water and oxygen, which Venus possesses only in parts per million. In August 2020, a month before the Cardiff team's announcement, a paper by Sarah Seeger in Astrobiology suggested a means by which life could exist in the clouds of Venus. She posited that, for life to exist in Venus at all, it must do so in liquid cloud droplets, Venus's case, within sulfuric acid clouds. While life on Earth can thrive in sulfuric acid, as said above, the acidic concentrations in Venus's clouds are 1 billion times stronger. It is possible that microbes might form a selectively permeable shell that retains water whilst expelling sulfuric acid. While water concentration in Venus's atmosphere as a whole is minuscule, 40 to 200 parts per million, within the acid droplets it is believed to be as high as 15%. According to Greaves and her team, phosphine appears present at Venus's equator, but absent at the poles, suggesting it is circulating within the atmosphere along Venus's giant Hadley cells. This is in line with Seeger's hypothesis, which suggests that as droplets grow, they eventually become too heavy for higher altitudes and fall toward the searing depths. As they do, the microbes within could protect themselves within spores, and then hatch once air currents carry them back to homier heights. Energy could be provided by exotic forms of non-oxygenic photosynthesis. But, you might of course ask, how could life have formed on Venus to begin with? Well, that answer may be fairly simple. Evidence is mounting that even as recently as 750 million years ago, Venus may have been a temperate water world like Earth. As the sun's luminosity gradually increased, Venus's oceans eventually dried up, and life, buoyed by the ever-thickening clouds, migrated upward to the planet's last habitable region. Now, if you, like me, are a watcher of these sorts of things, then you probably heard that the much-needed follow-up observations had thrown cold water on the initial result. While that is true, it's important to maintain perspective. A recheck of the Maxwell telescope result by NASA's Goddard Space Flight Center suggested that the initial finding was not phosphine, but sulfur dioxide, not an uncommon compound in Venus's atmosphere. But Greaves has responded that for sulfur dioxide to produce a spectral line like the one observed by the Maxwell telescope, it would have to not only be at an ambient temperature of 600 kelvins, twice the predicted temperature of the region of Venus's atmosphere under observation, but also be at a concentration double the largest ever recorded. And while the ALMA results were faulty, once recalibrated to account for a spurious spectral signal, they reduced the upper limit of phosphine detected from 20 parts per billion to 5 parts per billion, a number still 1,000 times larger than can be expected by abiotic means, and an error probability increase from 20 sigma to just 5 sigma, which is still less than 0.1%. And even if they aren't borne out, in October, another team using ALMA identified a second biomarker in Venus's atmosphere, glycine, the simplest of all amino acids. This is not the shocking revelation it at first appears. Glycine and other amino acids have already been found in asteroids and meteorites, and amino acid precursors have even been found in interstellar space. But the mere fact that something as complex and perishable as an amino acid can survive in the atmosphere of Venus at all suggests it may be more of a haven than we first thought. This has, of course, rekindled fascination with our wayward sister, and with NASA caught somewhat on the back foot, other organizations are moving in to fill the vacuum. In particular, a private company called Rocket Lab, which believes it can get a probe to Venus by 2024 for the bargain price of $30 million. We shall see. Whether these findings are biological or not, they have nonetheless worked a wonder. They have made Venus interesting again. For the first time in decades, hope has been kindled that our solar system's dark lady may be a mother after all.